Hello everybody, welcome back. Thanks for watching these videos. I hope they've been beneficial to you. If you have comments, please feel free to leave them in the comment section of the YouTube video. It's been fun for me too, I must be honest. I haven't taught in over a year. I have been on sabbatical for the last year, writing my history book. And so it's been a full year since I've been teaching, which is long time for me. I'm very passionate about teaching. So even though this is giving a little bit of, pandemic vibes, teaching to a camera, still, it's, getting me back into the flow of things, and I'm happy to be doing it. So I hope you're enjoying the videos as well. Okay, so next up is proposition 1.10 from the Proofs book. Now this proposition, again, it's in the Pigeonhole principle section. We will be using the Pigeonhole principle as the main tool to practice writing proofs. We have two forms of the Pigeonhole principle here. The simple form that says if you have more objects than boxes, and you put all the objects in the boxes, then at least one of the boxes must have at least two things in it. The general form says if you have more than k times as many objects than boxes, then one of the boxes must have at least k plus 1 objects in it. Okay, so that's the way to think about it. At least that's the way I like to think about it. This proposition is kind of interesting. It says this: given any collection of 10 points from a 3x3 square, there must be at least 2 of those points which are of distance at most square root of 2. Interesting. So oftentimes with these problems, it's good to do some scratch work. Because if you just read this, is it obvious where the Pigeonhole principle is going to appear? I don't think so. To me, it's not obvious. Now, at the end, we are saying we want to find at least 2 points which have such and such property. So that does suggest, the simple form of the Pigeonhole principle, the conclusion of it gives you 2 of something, 2 objects within the same box. So that is suggestive that we are going to be using the simple form of the Pigeonhole principle, but it's not conclusive. And either way, that doesn't really tell you what are your objects, what are your boxes. It's a little confusing. But let's do a little scratch work. I highly recommend when you're given a problem to immediately take out paper and a pen or pencil and start writing. Okay, you should. I think the brain works better when your hand is moving and you're actually trying to write. So just start writing down definitions that writing down the Pigeonhole principle again, drawing pictures in this case, because it's referring to a geometric square. So I would say start writing. That's going to get your brain moving. So that's good. So, if I were just confronted this problem, the first thing I would do is draw a picture of a square. We all know what a square looks like, but the problem refers to a square. So maybe let's draw a little square. That's a pretty good square. And it's 3x3, so I'd probably write some 3s on the side. And I've already written down the Pigeonhole principle right here. I've thought through, okay, the conclusion asks for 2 of something. Simple ends with 2, so most likely it's the simple form of the Pigeonhole principle that we will be using. And the proposition is pretty interesting. It says that if you have 10 points, I could do it randomly, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that there must exist 2 of these points that are only about 1.4 distance apart from each other, square root of 2. So let's see, which of these 2 look closest? Probably these 2, maybe those 2. So what it's saying is if you measure the distance between one way to think about it is your two closest points, that this is going to be no bigger than the square root of 2. So less than the square root of 2. That is what that is saying. Can you read that? Probably not. Anyways, that's what I did. I did a little, this distance, oh wow, now it's getting worse, is is no more than the square root of 2. Okay, so I'll just put that point back. Okay, so if you just look at these 2 points, they can't be more than the square root of 2 apart if those 2 are the closest points and this proposition is correct. Okay, so you might draw that down and think, okay, nothing's jumping out to you. You might try to think about the worst case in this particular problem. I don't know if this is going to be helpful, but this is something that I would probably do. I would think, well, how bad could it be? Sort of think about the limiting case. Let's put points as far away from each other as they can, maybe at the 4 corners. So that's 4 of the of the 10 points. And then you could sort of imagine, I don't know, the fifth one right in the middle, 6th one, I don't know, here, 7, 8, 9, something like this. And you could maybe measure some distances, see how far you're apart at this point. And the 10th, well, the symmetry is kind of breaking, but maybe somewhere down there. I don't know. So you could think about things like this and try to come up with some sort of reason why this would be the worst case, and even in the worst case it works, or something like that. That's one way to approach this problem. It's something that I would think about. That said, if this is the pigeonhole principle, if we're going to be using the pigeonhole principle, we need to come up with objects and boxes. Now, what are we given? We're given 10 points. If you were just to make a guess, would you think that those 10 points, they're probably either the objects or the boxes? It's a thing that you're given in the problem. Do you think they're going to be the objects or the boxes? Yeah, probably the objects. And if 2 things are in the same box, we want that to satisfy this property. They're not too far apart from each other. They're at most square root of 2 or something. Okay, so you're thinking maybe the points are the objects. If we're going to be using the pigeonhole principle, so maybe the points are the objects in this pigeonhole principle. In that case, what are the boxes? Well, in order to use the pigeonhole principle, you need more objects than boxes. The way it's actually set up is you need 1 more. If you had more than 1 more, that's fine, but 1 more is sufficient. So this, there's a little question theory going on here. If someone's asking you the question using the number 10, probably 10 is n plus 1. It's not n plus 3. Not always. Sometimes a professor might try to test your understanding by giving you more objects than you actually need, but nevertheless. So if so, then we would have 10 objects if this is the case. So we would need maybe 9 boxes. All right, need. Put some question marks because, this is just scratch work. I'm not really sure what's going on yet. Need 9 boxes. So if this is what you're thinking, where is 9 appearing in this problem? Do you see a 9 anywhere? Maybe? It's not there directly, but I wrote a 3 by 3 square. 3 times 3 is 9. Which means this has area 9. Okay. So a 3 by 3 square has area 9. ... So you see where we're going here? So somehow, if we take this square and chop up its area into 9 parts, then each of those pieces will have area 1, and each of those 9 parts could be our 9 boxes. Does that make sense? So that's one approach, is we could say, let's try to start with this square, chop it up into 9 pieces. Those are our 9 boxes. Then we have 9 of something. So this is at least an idea. You have 10 objects. Okay, how many boxes do we need? We need 9 boxes. Which of those boxes be? Well, we notice the area is 9, and then we wonder how to do it. And you could imagine how to do it. the simplest way is to have sort of 1 by 1 squares. So draw it as a grid. Is this clear? Yeah, that's reasonably clear. So chop it up as a grid. Then we have 9 1 by 1 boxes. So, do you see where the square root of 2 is coming into play? I'll step over here. That way I can do my animation over there. So I have a little animation. So in this animation, I take a 3 by 3 square. I add 10 points randomly. I really did tell the system to do it at random. The first one didn't look very random though, so then I did it a few times, and then eventually I got one that looked random. But nevertheless, it was one of these random asks that produced this. And then you take that and then you chop up your square into these 1 by 1, these 9 1 by 1 little squares. And then you ask the question, well, and then if you apply the Pigeonhole principle, you have 9 points being placed into, 10 points being placed into 9 squares. By the Pigeonhole principle, 2 of these points must be placed into the same square. Okay? And if 2 points are placed into the same square, question is, how far apart could those points be? Well, the furthest 2 points could be in a square is if they're on the opposite corners of each other. And how far away are the opposite corners? Testing your Pythagorean theorem knowledge. Square root of 2. Do you see? So this is the approach we're going to take in our proof. We're going to imagine, one small point is, what if the points, one of the 10 points, land exactly on the line between 2 of those squares? You have to say which square it belongs to. So that's a small point, but we have to do it because every point has to be placed into a box. So if it's in the middle of one of the squares, it's easy. Just put it in that box. But what if it's on the line between, which box does it go into? The answer is it can go into either one. So you just make up a rule that says, okay, it always goes into, if it's side by side, it always goes into the box on the right or the box on the left or something. Do you see? So do you have sort of a sense in your mind about where this proof is going to go? Okay, now let's take a moment and write up the proof. So I'll pause the video briefly and write on the board for a little bit. Okay, so in a course like this, one of the important skills to learn is how to understand mathematical statements, how to come up with proofs on your own. But another skill that's very important is how to write up your proofs. So don't consider the writing part to be extra, that you can basically hand in your scratch work and that would be sufficient. No, you should be able to write out your thinking in an organized and structured way that is logically sound and is very readable to whoever reads it. Okay, so here's how I started the proof. Divide the 3 by 3 box into 9 1 by 1 squares. And then I included a picture off to the side. Typically I'd put the picture like right below it at that point, but just to save board space, I put it off to the side. But pictures are good. Go ahead and use pictures in your proof, in your proofs in general. Now, using pictures is a little double-edged. It's good because it helps show what you mean, and it gives the reader extra help in sort of following along. But there is a risk that some pictures could be deceiving and could maybe capture one case of the problem, but not other cases, which you need to make sure the proof sort of logically works without any of the pictures, but still it's good to include the pictures to help yourself and the readers explain things. So pictures are good, just make sure that the proof doesn't rely on them from a logical standpoint. Okay, so we've chopped up our 3 by 3 square into 9 1 by 1 squares. And then we said regard the 10 points as our objects and the 9 squares as our boxes. So especially for these early Pigeonhole principle problems, it's good to sort of do this, say what are your objects, what are your boxes. Now, if you look up a research article that uses the Pigeonhole principle, they're never going to do that. They're just going to set up the problem, say, oh, 10 goes into 9, therefore by the Pigeonhole principle, blah, blah, blah. So even in most textbooks, once you get past the first few couple examples, if even then, they just sort of use it where you can sort of, they expect the reader to identify like, oh yes, of course, I'm not calling this the object, but by the context, it's clear that it is the object. But nevertheless, for now at the start, I recommend you actually spelling it out. These are my objects, these are my boxes. Okay, so I've identified our objects and boxes. This places the objects into the boxes, right? If you have 10 random points, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If you have 10 random points inside this square, then which box do I put this point into? Well, the box that it's in, right? So this action places the object into the boxes, except for this one point. What if one of the points lands right on the line between two boxes? Where do you put it? So you have to make up a rule. You can just make it up. Our rules can differ. It's fine. The rest of the proof will go through either way. But the rule I said is consider a point like that to be part of the box above and or to its right. So this point would be part of the box to its right. So that one. So that box now actually has 3 points in it. If you can see those points, I know on camera they don't appear quite as bold, but I'll make them a little bigger. So those 3 points ended up actually in the same box. Okay, so that's the setup of the proof. I've identified my objects and my boxes, and I've made it very clear how the objects are being placed into the boxes. And now it's time to apply the pigeonhole principle. If you place 10 points into these 9 boxes, by the simple form, the simple PP, simple form of the pigeonhole principle, at least one box, I'll be very clear, I'll say one by one square. So that's what the boxes are. Well, I said boxes here. I'll just say 1 by 1 box. Okay. At least one by 1 box will have at least 2 points in it. Okay. So there you go. So now we just have to conclude that these 2 points must be within distance at most square root of 2. So we just have to note that in a square, the farthest 2 points could be apart from each other are the opposite corners, and the distance of that is the square root of 2. And these 2 points can be at most a square root of 2 apart. Because that's the max distance between 2 points in the square. Between points in the square. And I'll draw a little picture showing that. So we have points on opposite corners. Then their distance would be square root of 2 apart. End of proof. Okay, so, this is, I was going to comment, this is an example of a proof from chapter 1 where couple details are kind of ironed over. You know, I'm not going to actually write down a proof that the opposite corners are going to be the furthest 2 points away. Hopefully that is intuitive to you. In a very ironclad proof, you would include some sort of justification for that. And there are ways to do it, but we won't get into those details here. The point is to get a little bit of muscle memory of how to come up with an idea, how to write out the proof, appealing to the pigeonhole principle, and so that's where I will leave it at this point. Okay, so that is the next. That was proposition 1.10, and I believe there's yes, this is a fun one and a challenging one. Okay, so the next one is challenging. It's also one of Paul Erdős's favorite problems, if you've heard of Paul Erdős. He used to give this one away a lot. So, okay, so tune in next time to see another very fun problem from the great Paul Erdős.